You ever wonder how your phone's AI can follow a long conversation, or how translation apps make sense of a really complex sentence? Well, it all comes down to memory. And the blueprint for that memory, believe it or not, was drawn up way back in 1997, long before AI was a part of our daily lives. We're going to break down how this one single paper, well, it pretty much taught machines how to remember. But to really get why this was such a huge deal, we have to understand the problem they were facing. For early AI, just remembering the beginning of a sentence by the time it got to the end was a massive, almost impossible challenge. So, what was stopping them? So, here's our roadmap. First, we're going to dig into AI's big memory problem. Then, we'll uncover the brilliant solution, a special kind of cell that has its own memory. After that, we'll look at the secret sauce, the power of gates, see the mind-blowing results, and finally, we'll trace its legacy all the way to the AI that's probably in your pocket right now.
All right, let's dive right into that core challenge. They called it the problem of vanishing errors, and for a long time, this was the brick wall that researchers just kept smashing into.
You see, the first attempts used something called a recurrent neural network, or an RNN. The idea behind it was actually pretty simple and kind of elegant. As the network reads a sentence, for example, it feeds a little bit of information from the word it just saw back into its calculation for the next word. It creates this loop, right? A sort of primitive memory of what just happened. And for a while, it seemed promising for stuff like speech processing. But, and this is a big but, there was a massive flaw. As the authors put it so perfectly right in their paper, the error signals that the network uses to learn, well, they would either blow up and create total chaos, or, and this was the much more common problem, they would just vanish. And this is such a great way to visualize what was happening. Okay, imagine the AI is reading a long paragraph and makes a mistake because of a word it saw 100 words ago. The correction signal, the thing that tells it, hey, you messed up, it starts out really strong at the end, but as it travels backward through the network, step by step, it gets weaker and weaker, like a fading echo. By the time that signal gets all the way back to the source of the original error, poof, it's gone. The network literally has no idea what it did wrong, so it can't learn from its mistakes if they're too far in the past. So, what do you do if your signal keeps disappearing? Well, you don't just send it down the same old path. You build it a brand new, protected highway. And that leads us to the big breakthrough, a specially designed cell with its very own memory. They called it long short-term memory, or LSTM for short. And honestly, the name tells you everything you need to know. It was designed to hold on to important information for a long time, bridging those huge gaps while still processing all the new short-term stuff coming in. It was built from the ground up to fix that vanishing error problem once and for all. You know, the best way to think about an LSTM cell is to imagine a person with a little notepad. The memory cell itself, that's the notepad, where you can jot down important bits of information. But here's the clever part. You don't just scribble down everything you hear. You have rules. You've got an input gate that decides, is this new information important enough to write down? And then you have an output gate that decides, okay, is now the right time to read from my notepad and share this info? And this idea, this concept of gates, this was the secret weapon. They were the intelligent traffic cops for the AI's memory. At the very core of this whole thing is what the authors called the constant error carousel. Now, it's a fancy name, but just think of it as a perfect little conveyor belt. Any information you place on this conveyor belt can travel across hundreds, even thousands of time steps without fading or getting messed up. The vanishing signal problem? Solved, because the signal now has its own protected VIP lane. So here's where it all comes together. The gates are the ones managing this special conveyor belt. The input gate is like a bouncer at a club. It protects that valuable information on the notepad from getting overwritten by useless junk. It only opens the velvet rope when something truly important comes along. And the output gate, it does the opposite job. It protects the rest of the network from the notepad. It only shares a memory when it's actually helpful, so it doesn't distract the AI with irrelevant facts at the wrong time. It's just a brilliant system of checks and balances.
Okay, so the theory sounds amazing, right? But did it actually work in practice? Let's take a look at the proof.
Oh, it worked. And I mean, it worked spectacularly. In their experiments, LSTM was able to connect a cause and an effect separated by more than 1,000 steps in time. 1,000! Now remember, the old models were failing at just 10 steps. This wasn't just a small improvement. This was a complete game changer. And this table just lays it all out so clearly. Look at the standard algorithms.
total failure after only 10 steps. But LSTM, it cruised past 1,000 steps with no problem, even when they deliberately flooded the experiment with thousands of distracting, irrelevant pieces of information. The gates were doing their job, and they were doing it perfectly.
The conclusion was just undeniable. The authors had built an architecture that could do what was previously thought to be impossible. They had solved the long time lag problem, period. So, awesome result for a niche paper back in 1997. But why are we still talking about it today? Well, this is where we get to see the incredible legacy of this one smart idea. Seriously, just think about it for a second. Speech recognition on your phone, AI tools that compose music, Google Translate, even the chatbots that are everywhere now. The fundamental ability to remember context over these long sequences, which is absolutely essential for all these things to work, has its roots right here in this paper. LSTMs became a foundational building block for the entire AI revolution that came later.
And that's really the big takeaway here. This was never just about remembering a word from the beginning of a sentence. It was about remembering the context. And that is the crucial difference between a machine that just processes words and one that can actually begin to understand language. LSTM gave machines a working short-term memory, and with it, the first real glimmer of comprehension. So, that 1997 paper solved a critical piece of the puzzle. It created an artificial memory using these ingenious gates. Which, of course, leaves us with a really fascinating question for today's researchers. If intelligent gates were the key to unlocking AI memory, what's the next mechanism we need to discover to unlock the next great leap for AI? Genuine common sense?